So we are going to say a few things about the alternating current circuits, AC circuits. As I have said before, we are not going to go deeply into that topic because that has to be done in a different course. In this course, we are going to see a few fundamental definitions. So we are going to see some concepts, and typically we are going to see how an alternating current circuit behaves typically. As a result, this is a circuit where the EMF depends on time, and it just changes with time in a sinusoidal way. So that's sinusoidal. Depends on time in a sinusoidal way. So that also implies that you choose a direction on a circuit, and along that direction, so the EMF is sometimes positive and sometimes negative. Right, that's our circuit symbol for the EMF device, an AC EMF device, of course. As a result, we are going to see what happens if I connect some circuit elements to these devices. So the first question that we might ask, why AC? Why we need to use AC in our houses? This has actually some interesting historical background. There was something called the War of the Currents between Thomas Edison and Westinghouse. So different companies fought over this thing, but eventually the AC circuits somehow won. So the essential idea in here is that this type of current is more suitable for transferring energy from power plants to our houses, so you can then have actually a minimal loss somehow by doing some certain energy conversion. By using some transformers, you can do that. Let's also remember that in power plants, the first EMF is produced is basically in that way. So we have some certain a frame of wire which is rotating with constant angular velocity inside a magnetic field, and we have seen that in that case the EMF produced would be a simple AC EMF. So that's the one that we are actually carrying in here. We are using in our houses. So as a result, let's just start with this. So therefore, the EMF has a sinusoidal time dependence, so we usually write this time dependence like that. And so this function is either a sine or cosine. Don't worry about which one you should use, because I can express the same thing in terms of the sine function by a simple shift of that phase angle in here. So I'm just going to write this thing down in here, but I'm also going to show at some stage how to get these kind of functions. So as a result, by changing this function to from cosine to sine, all you need to do is to change this phase argument. So just keep this in mind. So therefore, there's nothing special about cosine, because sometimes some people want to use cosines and some people want to use sine function. So the coefficient that appears in here in front is called the amplitude, and the angle that appears in here is called the phase. So with this, the EMF has this kind of a time dependence. So I'm going to draw it like that. So let me use a different color in here. So let's say a yellow color. So we have this maximum value of the EMF that is attained periodically. So the maximum value is equal to the positive value of the amplitude, and the minimum value is the negative value of the amplitude. So therefore the EMF changes between plus epsilon 0 and minus epsilon 0. So just keep this in mind. There's also a phase argument in here. So what happens to the phase? So phase essentially changes this initial value of this thing in here in a way Or you can think of it like that, it just changes or shifts that curve to the right or to the left. So as a result, with a different phase, you would have this kind of a curve, for example. It will be just phase shifted. So usually the phase is not important because of the basic reason that the time also is something that you can measure starting from any point in time. So as a result, if I, for example, choose my time t equals 0 at this point, by just changing when I start my clock, I can change the value of that phase. So as a result, I can start my clock in such a way that this phase angle is equal to 0. So as a result, if I choose my origin in here, time origin in here, in that case, for this kind of a thing, I should have the phase angle to be equal to 0. So therefore, this is something that you can adjust. But there's something else in here. There's a phase difference. So as a result, I don't know, if you are talking about the EMF or the EMF and the, I don't know, the potential drop on some circuit element, so these are going to have different phases, perhaps, by using the same time scheme. You can change the phases, but you cannot change the phase differences. So usually, we don't talk about the phases, but the phase differences. The phase differences are the important ones. So we will be basically talking about phase differences frequently. So just keep in mind that, for example, the phase of the EMF can be chosen arbitrarily. You can set it to be equal to 0. But depending on the chosen phase, the other circuit elements or other quantities might have different phases. So it's something that you cannot get rid of entirely. So just keep this in mind. So what happens? So for example, we have a circuit like that. So we have an alternating current circuit. So it's connected to something in here. That something may contain lots of different things. So it might contain a resistor, an inductor. So this is basically what we are going to see, and a capacitor. Or I don't know, instead of this, I might have a parallel connection of the resistor and a capacitor and an inductor, perhaps. Or we might have a more complicated circuits like, I don't know, so there might be another resistor in here and a capacitor in here and so on. So in any case, that would be a very complicated AC circuit. But of course, in here, we are just going to see only the series RLC circuit. So we are just going to see this. So before starting with this, of course, we are going to investigate the behavior of each individual element, circuit element in here separately. So we are going to talk about what happens if I just connect a resistor, if I just connect an inductor, and then just a capacitor. So just keep this in mind. So in here, of course, we can then talk about the EMF of the EMF device. We can also talk about the current in here. And we can perhaps talk about the potential drops on some circuit elements like the capacitor or the inductor and so on. Again, I have just said something about the potential concept for inductors. I have said that this is usually meaningless, but because there's actually an EMF in there, so we cannot define the potential difference in there. But usually when people are doing these kind of circuits, they just forget about this kind of a detail, and they just show this thing as a potential drop. So we will also talk about these kind of things. So I'll just start with the EMF and the current. So EMF has a expression like this, cosine omega t plus phi, and the current has also as an expression like cosine of omega t plus phi prime. So we have amplitudes and we have phases. So as a result, the EMF is going to have this kind of a time dependence, but the current is going to have this kind of a time dependence. So it is expected that there is some kind of a phase difference between these two. That essentially means that whenever the EMF becomes maximum, the current is still changing, and whenever the current becomes a maximum, the EMF is still changing. So as a result, first one of them becomes a maximum or a minimum, and then at a later time, the other one becomes a maximum. So in any case, that time difference is basically related with the phase difference. So delta phi in here is the phase difference in here. So we are going to see that this time difference or the time lag between these two functions is related with this phase difference. So we are going to find that relationship. So as a result in here, for example, in these kind of circuits, that's one of the things that we are worried about. What is the phase difference between the current and the EMF? And the second thing is that, for example, what is the relationship between the amplitude of the current and the amplitude of the EMF? I don't know, the other quantities as well. So for that reason, the AC circuit devices are slightly more complicated than DC circuit devices. In the case of DC, we just found a relationship between these two, the EMF and the current, or the potential drop and the current. But now we also need to talk about the phase differences. Right, let's see. So omega in here is the angular frequency. So let's just remember that this is in radians per second. We can also write this thing down as 2 pi times f, where f is the frequency. So therefore, this is in basically unit is 1/second. So that's the same thing as hertz. So we just show this as Hz symbol. So in our circuits that we use in our homes, this frequency is 50 Hz. So that's basically the standard. So that means the omega is like, which is 2 pi f. That would be about 310 radians per second or something like that. So of course this is not always entirely stable, so therefore I'm not writing all the digits in here because not all of them would be significant. So let's just keep this in mind. And then there's another thing. Let's just talk about an EMF device connected to a resistor. All right, let's just make this a little bit more general. So suppose that we have some other circuit elements as well, and all I'm interested in is in the potential drop in here. So let's just forget about all the other details in there. So let's just talk about the current and the potential drop in here. So let's say that the current is equal to I0 times cosine omega t plus phi. All right. So the potential drop in here, basically, I'm going to write it down like this. This is point A and this is B. When I say potential drop, it's always is this. You're moving along the direction of the arrow in here. There's an arrow always to express things. And if you see that the potential really drops, the potential drop is positive. So that means if A is bigger, has a bigger potential than B, that is VA minus VB. If this is positive, then the potential drop is positive. So let's just keep in mind that for a resistor, the potential drop is always proportional to the current. So if the current is positive, then the potential drop is positive. So therefore, for a resistor, the potential drop is equal to R times I0 times cosine of omega t plus phi. Right, so the first thing is that for a resistor, therefore, the potential drop and I have same phase. And the second thing is that, of course, let's say it like this, VR0. So that's the amplitude of VR, the potential drop on the resistor. That's simply given as R times I0. So that's the Ohm's law. So I'm going to show it like this. This is the Ohm's law. So this is the simplest kind of circuit. So we are going to see that if there are some other devices like the capacitors or inductors, we will have more or less the same thing, except that of course the phases will be different. And we can still write down Ohm's law, but in that case we have a different expression in here apart from the which is different from the simple resistance. But let's talk about the power. Right, this is the power of heat produced on resistor. So that power is, so I'm going to call this as PR, is simply given as the current multiplied with the potential drop. So that's always the case. That's the amount of the energy that goes into a device. But now this is time dependent because both the current and the potential drop dependent are time dependent. So therefore this is like I0 cosine omega t. Sorry about that, multiplied with VR0 cosine omega t. So at the end we get something like this. This is product of the amplitudes multiplied with the square of the cosine. So therefore the power is also time dependent, but it has a different time dependence in here because this has to be always positive. So I'm going to draw a graph like that for the time dependence of the power. So it has a time dependence like that. The phase is irrelevant in here, so that's not that important. So basically, this is instantaneous. The power changes between 0 and its maximum value, which is I0 multiplied with VR0. Right, so as a result, I don't know, if you are using, for example, hair dryer, it uses power like that. So as a result, there are some certain moments where your hair dryer uses 0 power, and at some points where at some times it uses maximum power. But usually, I mean, this time difference is very small. It just happens in a very quickly, so it's something that you don't notice. So this thing basically changes, I don't know, 50 or 100 times within 1 second. So as a result, when you are using hair dryer, of course, you don't notice this change in the power. So as a result, from our perspective, the instantaneous power is irrelevant. It's not that important. What we are interested in is the average power. So it's basically averages. I'm going to show this with a P bar symbol. Average power. You just basically take the average of all of these. So that's the time average. So in here, if you have a time dependence like that, it's the square of a cosine or a square of a sine function. It appears that this square basically changes between 0 and 1. And so therefore its time average is basically 1/2 of it. So it's basically it's the arithmetic average of this maximum value and the minimum value because there's some kind of a symmetry between this thing around the midpoint. So as a result, the average power in here is equal to 1/2 of I0 VR0. So that's kind of important. So as a result, I'm going to do it separately again. So I'm talking about the for example, the function sine omega t. If you talk about sine squared omega t, so that's sine squared omega t, we have sorry about the sine squared, starts from 0. So it's a function that changes between 0 and 1 in a periodic way. So it changes between 0 and 1. And we're not interested in this, but we are interested in its time average. So that means, I don't know, you just take a very long time. So you just take this function sine squared omega t, integrate this for a very long time. So I'm going to write t long in here, and then divide by that long time. So that's the time average essentially. In general, for functions, let's say, if you integrate it and then divide by the time interval, that's essentially the average area under this curve. So that's basically what we should be talking about in here. But this thing is equal to 1/2. So that's essentially, you can think of it as the arithmetic average of between of 0 and 1. So therefore, this is 0 plus 1 divided by 2. Right? You can also think of it like this. I can think of sine squared omega t as this is 1 minus cosine of 2 omega t divided by 2. And if I take the time average of, this is just a trigonometric formula, half angle formula. So let me first write this expression in this form, cosine 2 omega t. So if I take the time average of sine squared omega t, so therefore this is equal to the time average of the first term, which is just a constant, so its average is equal to 1, and the time average of cosine function. So the argument is not important. We know that the cosine somehow symmetrically changes between positive and negative values, so therefore its time average is equal to 0. The time average of 1/2 is 1/2, so obviously then, therefore, the time average of sine squared omega t is 1/2. All right, so that's one of the things that we actually use a lot. So if we have a sinusoidal time or position dependence of anything, and if you are taking the average of the square, so the sine squared has an average value of 1/2. So therefore, we just draw this curve in here. This is just the arithmetic average between the maximum and the minimum. Right. So as a result, for the resistor too, we can also say the same thing. And so for this reason, we are going to talk about this. So that's the average power. Right. Average power of heat dissipated or consumed on a resistor. So this power is, the average power is on the resistor, whatever. So it's basically 1/2 of the maximum possible power. So on a DC circuit, of course, we would not have this 1/2 in there, because the current would always be equal to I0, and the potential drop would be VR0 all the time. But for an AC circuit, we have a 1/2 factor. So as always, I can also write this thing down in terms of the current only by using the resistance as a variable, or the potential drop only. So therefore, I can write this thing down as VR0 squared divided by R. Right? This is as simple as possible, right? We have these, I don't know, 3 formulas, essentially the same as the DC formulas, but there's an extra 1/2 factor. That's something that you need to remember. Unfortunately, people get confused by this 1/2, so as a result, they have a definition of the amplitudes. So instead of amplitudes, they use something called an RMS value. So the RMS current is basically defined as amplitude of the current divided by the square root of 2. So RMS means root mean square, and you have to understand it in the mathematician sense. you have to think of this as functions. So it's just a function composition. So first you take the square of the current. So you have a current which is time dependent. So you just first take the square of that current. So let me write it down like that. So you just take the square first. And then take the mean of the square. So you just take some average of it. And then after that you take the square root of it. So therefore this is the square root of that. So that's basically the RMS current and the RMS value of the current. So for the current, of course, the current is equal to I0 times cosine something. So the square of the current is I0 squared times the square of the cosine. Okay, so the mean of the square is I0 squared times 1/2. And the RMS value, which is the square root of that thing, so that's I squared t average and square root. So that's going to be equal to I0 divided by root 2. Right? That's essentially what it means. So the RMS value of the current is defined as, it is defined like that, so that's the formal definition. But if the current changes sinusoidally, in that case, the RMS current is basically amplitude divided by root 2. So what's the advantage of this thing? It's basically very simple. What's the advantage is that you can then express the average power in a way that is as if you have a DC current and DC voltage. So that's basically the power that would be produced on the resistor if there was an DC current whose current value is equal to that RMS value. That's essentially, this is what it is. But just keep in mind that people actually use the RMS values all the time. And so as a result, in that case, you can write down these formulas like that. So you don't have a 1/2 factor in such kind of a situation. Right? So just keep in mind that, for example, the RMS value are the one that are actually usually reported on, I don't know, hair dryers or whatever, all the household devices. So you should keep in mind that also we are using 220 volts of AC electricity, and that essentially means that the wall plug in your homes is actually an EMF device, and the RMS value of the EMF coming from there is actually 220 volts. So that essentially means the amplitude is basically root 2 times bigger than this. So it's like 1.4, so that's going to be about 310 or something volts or something like that, or 300 volts. I don't know, it's just an approximate value. So let's just say that this is 300 volts. So the amplitude is actually much higher, but people usually always report only the RMS values because they want to save people from dividing these products by 2. So that's the biggest advantage of that notation. So as a result, from time to time, of course, we are going to use this RMS concept